Well, this is an important session because hopefully everyone will take stock and listen carefully, because we're going to talk about what we're going to be doing under our current plans for the simulated ground motion database. And as I think about this, and I'm going to look back at Matt's talk, he started to begin a very important discussion about what format we should have some of that data in for a multiplicity of users. And he talked about the notion of, maybe people still want to do a one-dimensional site response calculation on their own. They have nonlinear codes for site response. Maybe we want to give them bedrock motions, a rock outcrop, or in-column motions as opposed to surface motions, for example. So that leads to a very, very important discussion. And as we think about these simulated ground motion databases, we hope that this is the beginning of a long-term discussion, and we're not locked into anything we're going to talk about today. Today is simply a first realization, or thinking about a first realization. So I'm going to talk about EQSIM. I talked about it a little bit yesterday. I'm going to do the next click down today, because we have to understand what the current simulation capabilities are as we begin to think about motions we're going to be generating. Are they sufficient? Can we do outputs that people can use in different formats, etc.? So I'm going to go into a little bit of that quickly with a little bit of detail. I'll be followed up by Arben, who's going to talk about our rupture scenarios that we're going to have in this first realization of the database. And then Floriana is going to tell us all about the verification and validation of the motions, which is very important. If you recall in my talk yesterday, I said under the current DOE project, I had clicked two boxes. One is generating a database, the first realization of the database, and one is developing an acceptance criteria. So we're going to give you an update on where we are with each of those. Just to remind you, those that weren't here yesterday, the EQSIM framework is about the ambitious goal of going all the way from fault rupture, propagating energy through the earth, and then intersecting in an appropriate way that energy arriving at a site with the infrastructure system that's at that site. And this is just a cartoon of that problem. This is really, really a tough problem computationally. It's multi-scale. We're often looking at regions of hundreds of kilometers, and yet we want to get those motions down and have them interact appropriately with an infrastructure system that may be 30 meters or 40 meters of dimension. And so that is truly a multi-scale problem. As I've indicated on the bottom, as we go through this path from source rupture to the final structural response, we cross a number of disciplines, right? We start with seismology, the generation of the source function and the propagation of the waves in bedrock. We then typically have to go into a geotechnical domain where we worry about site response, and then finally we worry about the structural response. So it really is cutting across three different disciplines there. It's worse than that, though. This computational challenge is so great that we have to pull in people that are really, really good at algorithm development and computer science if we want to be most effective in this. This is just with these new brand of machines and GPU accelerated machines, new architectures, we're really going down a very poor path if we don't pull in the real experts that understand how to make those machines work very well. As consequently, our team has been highly multidisciplinary over the last 6 years, and I'm just showing you the contributors here. We've had people in engineering mechanics. We've obviously had seismology and geophysicists. Just as important, we've had computer scientists that really understand how to make these new architectures work very efficiently in massively parallel mode, and understand how to deal with 200 terabytes of data from a single simulation. That's really, really an important challenge here. So we really need computer scientists, and then we need applied mathematicians and numerical folks that can really tune our algorithms, make them work very, very well. High order algorithms and algorithms that work well in parallel. Then we've had, you've heard from Maha yesterday, we've been lucky to have a whole cadre of postdocs and early career scientists that have contributed to this. And often they're the ones down working in the trenches and having the fun because they're looking into the applications. And so we've really been lucky to have a large group here that is quite good. So let me just tell you what we've done and the implementations we've made. We started with SW4, which is a fourth order in space and time summation by parts finite difference code that was developed by Anders Peterson at Lawrence Livermore National Laboratory. The reason we did that is Anders is an applied mathematician. And he is very, very rigorous in how he thinks about algorithms and validation of code. So we wanted to start with that code because it's a high order code and it had a really, really strong theoretical foundation to it. So we've started with that code, but over the last 6 years and over the course of the project, we've done a whole bunch of things to move this forward and become efficient for the domain we're working in. We've done a lot with mesh refinement. I'm going to talk about that in a minute. Recall, we're trying to do direct broadband simulations. We cannot use a regular grid throughout our domain. We have to have a grid that is in tune and copacetic with the natural variation of the geologic properties, or we can't even begin to move forward. So we've done a lot of work on mesh refinement. You're going to hear from Hujun Tang this afternoon. He is an expert in I/O. And so we have redone all of the I/O entirely within SW4 and made the I/O based on HDF5 datasets all the way through our workflow, and it's a very consistent way. We've had to develop compression algorithms for our data. These data sets are huge. The good news about simulations is we get a lot of data that's very dense spatially. The bad news about simulations is we get a lot of data that's very dense spatially, because that creates huge data sets that we have to deal with. And so I/O has been a very important problem. Readiness for GPU-based platforms. These are entirely new architectures. I mentioned DOE's motivation yesterday in starting the application development early. So these applications were prepared and came along with the maturation of the GPU accelerated technology. So we had to deal with that. And then we've always, we rely on the Grace-Patarka source model. And so we've done not only some science enhancements to that, we've done a lot of economizations in terms of the computational aspects of that model. We're dealing with really, really large sources, that can have millions, literally millions of point sources. And so we've really worked to make that computationally efficient in our workflow as well. You look on the bottom, I see some other applications there. And I mentioned yesterday that not only was DOE inventing applications, but in the spirit of developing the whole ecosystem, they were developing new software technologies that all of the applications could draw upon. And so we use three. We use something called Raja, which is also developed at Livermore. That is a set of C++ libraries that help you translate to different platforms very seamlessly. And it eliminates the need to do a lot of reprogramming of your inner loops in your computational algorithms. And so we use Raja. We use HDF5 now exclusively. A lot are familiar with that. And then we use something called ZFP, which is a compressor for data, a very rigorous compressor. And the principle behind that is when you get these very, very large grids with billions of grid points, when you have two nearby grid points, the numerical values at many instances of time are numerically very similar in terms of the mantissa and the exponent. We can exploit that. And we can eliminate some of the double storing of those values, and so we use the ZFP compressor. So that's all part of the ecosystem. We put a lot of time into this hybrid grid generation and optimization. The current model in SW4 uses a curvilinear grid in the near surface so that we can map to topography, automatically maps to the topography from the USGS topography file. And then when we get down to depth, we transition into a Cartesian grid, which is very, very numerically efficient. Why? And not only do we do that, we also now have the capability for doing transitions and grading that grid. And so we can start with a very fine grid in near the surface to capture those short wavelengths and soft sediments. Then as we get down to depth, we can extend the size of those elements in an effective way. This took us about 2 years of development. If you think about this, it sounds conceptually simple, but this gridding technique has to maintain the fourth order accuracy in space and time of SW4. So there we need the rigorous algorithm development. And we also have to map this across the fault itself. And so it's not a trivial exercise to implement this kind of a mesh refinement, but we got there and it's been very, very important. Because we're so focused on this end-to-end capability, we've put a lot of work into understanding and developing a couple of options for interfacing the geophysics model, the global geophysics model, with our local engineering model. So we have two options embedded in the code currently. One is what we call weak coupling. We just take the surface motions coming out of SW4 and we apply those in a fixed-based sense to the structure that we're analyzing. And so just like you would do when you get a real record and apply it to your structure. Then, in addition, if you recall in our objectives I mentioned yesterday, one is to get a better understanding of the regional scale of motions. Another is to get a better understanding of the interaction between the incident seismic waves and the infrastructure system in terms of, what if we have inclined body waves and surface waves? What are the limitations of a 1D site response calculation in that case then? So for that, we have completely implemented and tested the domain reduction method developed by BLAC. And as you know, that allows us to take the geophysics model quantities at the boundary and apply those in a consistent way to the local soil island that completely honors the complexity of that incident wave field and its response on the structure. So we've done that as well. To do that, again, it's easily said, and it's not so easily done because we're dealing with these really giant data sets. So we had to optimize our schema for doing that as well. So what I'm showing you here is we have a very, very large regional model. Suppose we want to apply the DRM to any location here. So we've gone through and developed an algorithm so we can zoom in on the geophysics model just in that local domain. We can set up a bounding box. We can take those discrete grid point values of velocity in that box and do a spline function interpolation. So we get a continuous velocity field in that little cube. And then we can immediately, simply, by having the coordinate systems of the global model and the local model oriented the same, we can immediately then get the DRM boundary values in that domain. So that's been the simple algorithm, not simple, the efficient algorithm that we've done. So this allows us to do two things within the current construct of EQSIM. We can run a DRM like we see on the top, so we can account for all those effects. We can have a nonlinear soil model there locally. We can do that. Secondly, down on the bottom part, if we have a small basin or sedimentary basin, we can isolate that basin and put in a different constitutive model as well. So that's the extent of what we've done with respect to the DRM. We talk a lot about the computers, and we spent a lot of time talking about Frontier, but in point of fact, the DOE exascale ecosystem is more than one computer, it's multiple computers. They're all GPU accelerated. What I'm showing you here, there's a Perlmutter computer of 71 petaflops up on the hill. We use that for a lot of our structural calculations. There's the Frontier computer at Oak Ridge, which has been certified to be 1.1 exaflops. And there's a new computer coming online at Argonne that's going to be about 2 exaflops. It's projected to be about twice that. This is all interconnected through the engineering science network, which is a huge, fast optical data pipe. And so I'm just showing you, for example, some of the statistics over here. We can transfer, in the methodology we've developed, 267 terabytes of data, which corresponds to 942 billion earthquake time histories in about 8 or 9 minutes over that huge data pipe, optical data pipe. So this whole network is now becoming available. And so the EQSIM workflow is not implemented on a single computer, it's implemented on multiple systems. And we can mix and match those systems to work most efficiently for the task at hand. So for example, in the ground motion simulations where we're talking about billions of grid point models, we have to do that on the big iron at Oak Ridge on the highest fidelity models. We generate the ground motion data there. We move all that data, for example, to Lawrence Berkeley Lab, where then we can mix and match and do the structural evaluations of different modalities that we want to do. And so the ESNet transfer of that is important. Then finally, you're going to hear a little bit about this afternoon, huge data sets. How do you inspect and interrogate those data sets? And so you're going to hear about a tool called EQSIM Viz, and that allows us to pre-compute movies and ping files of ground motions so that you can go in and inspect those very rapidly, interactively on a Google Map background. And so those are the 3 components of the EQSIM workflow as it currently exists. This is just an example in the San Francisco Bay Area, sort of an end-to-end evaluation. You can see the earthquake start. This is a 391 billion grid point problem at 10 hertz. And on the right-hand side, you can see a local model coming from open seas with a DRM boundary, and it's right near field, so you can see how hard that DRM boundary is working to impose those permanent displacements and large displacements on that model. And you can see we've developed some color coding so that we can post-process the results and get a visual image of the damage, potential damage based on peak interstory drift in that building. So in June, the Frontier computer finally came online, and we were able to get on it. This thing is a beast. It's 9,400 compute nodes. And so you can fit a really, really big problem on this. So I'm not going to go into a lot of the performance, but I'll offer this one slide. This goes back and shows every single simulation has been performed, earthquake simulation, regional simulation in the San Francisco Bay Area, starting in 1999 with Steidem et al. And what we've done is we have come up with a measure of computational effort. You can see it on the bottom. I don't have time to go into it. But these models are all different sizes, and they're different frequency resolutions, and they're different V sub S min cutoffs. So we've come up with a consistent way of measuring the computational effort. So what do we see? The computational effort is on the vertical axis, and the year is on the right-hand side. The color dots, the multicolor dots, are all historical simulations of the San Francisco Bay Area, the computational effort for those, and you can see that trend. Now, you can see the trend to the blue, where we begin to get on these GPU-accelerated systems with this optimized software, and we're on an entirely different tangent in terms of performance. But if you look at this, this speaks to, in my mind, why we're posed on the edge of an era where we can really begin to use simulations, broadband simulations, because we can do these computations very, very big and very, very fast. So that's an important element of this. So for the Bay Area, our first realization, we are going to create 25 Hayward fault rupture scenarios. We're getting close to being done with that. If you look on the right-hand side, we're going to spread out and do the hypocenters at 5 different locations. And then Arbin is going to turn the knob on the Grace-Patarka rupture model at each of those locations and give us a different distribution of slip. So that is coming. This is generating really, really big data sets. And so any synthetic ground motion database must be thought of in terms of scalability as we go forward. We're doing 5 Hz simulations now. We'll want to increase that eventually. What I'm showing you here is the storage demands of what we're getting to. So on the vertical axis are the storage requirements in bytes. This is the number of ground motion sites. This blue line represents the data that is required for a 10 Hertz Hayward fault simulation with a V sub S min of 140 meters per second, which we can do readily now. To do that problem as a function of that low V sub S min on the bay margins, we've been talking about this, our discretization is 1.75 meters, and there are 3.14 billion surface grid points. So that equates to 3.22 petabytes of data. It's a lot of data. So ultimately what we're going to do is store that kind of data from these really big simulations at the National Lab, but for PEER, we're going to do 2 things. We're going to downsample that data. You don't need data generally at 1.75 meters. We're going to downsample it initially to 1 kilometer or 2, and then transfer that data to PEER to embed in their database. To put this in perspective, this is the size of the current entire PEER NGA database here at this dot now. So this sort of points to the character of this challenge with respect to data. This is just surface points, so we have to balance this when we start thinking about developing a volume of motion so people can apply DRM robustly. So there's a lot of thought, the point of this is, and going into this database, of how we manage this very, very large data flow. EQSIM, I think you'll get a demonstration this afternoon. One of the things we've developed, which has been very, very powerful for looking at these motions, is how in the world do you go through and inspect this kind of data? So what Hujung Tang came up with is we use a server at Lawrence Berkeley National Laboratory, which is developed just for displaying large data sets. We pre-compute in parallel ping files of all our components of ground motion time history, as well as movies of the animation of the building response, if we want a building response in the wave propagation. We stuff that all into this server, data server, and then there's a window. EQSIM is a specialized software that Hujun has developed to come up on a Google background, and you can roll your mouse around and you can click and point, because all of those figures are pre-computed. They pop right up. So it's very, very highly interactive. So if you want to run down the Hayward fault and say, do these motions look realistic? Do they look like they have the right fault normal pulses or fling step? You can just run down and go click, 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 click with the mouse like you're seeing over here in this cartoon and check those. So that's been an important thing and a very important part of this end-to-end workflow. So you're going to hear more about this afternoon. The intent is PEER, and this came out of the 2021 workshop. PEER will strive to make the simulated ground motions as familiar as they can to the user community in terms of interface. And so that's, Holland will have more to say about this. So the idea is you have the NGA database. This database will be stood up in parallel and provide access. So when Matt was discussing a very important point, and this is where we need to think about our simulation and our use cases. You know, there's a number of different ways we might want to end up ultimately setting up this database. Right now, we are just modeling in a linear sense the geotechnical layer, I'm going to call it geotechnical layer, and rock, and we're giving a set of surface motions for that. And people can use this in multiple ways. You know, we heard yesterday about applying empirical factors for site response, so forth, that's fine. We can then give a near surface volume of motions that people can access and run a DRM type calculation if they so desire. But it's not unthinkable that we could also, and many in the geotechnical community are still going to use a 1D site response calculation, most likely. As Matt was alluding to, we could give in-column motions here at some defined point where people could do a 1D site response calculation, or we could even scrape off the geotechnical layer and give rock outcrop motions. So all of those are within the realm of possibility as we move forward. So I'm going to end by just saying, you know, this, I think people are going to have fun with this. It's really a rich data set. I'm giving you an example here of a little bit of exploration we've done. This is looking at within event variability for a magnitude 7 Hayward Fault earthquake. Same identical building located at sites A, B, and C, shown on the map on the left. This is for a northern hypocenter. And identical building, same event. We wanted to get a handle on how much variability there could be for that particular structure, which is important for engineers to understand. If you're designing to a median value, you kind of want to know what those bookends are and what the tails of the distribution are, right? Is that building still going to be damaged? So you can see here, and this is showing the ASCE limit states for steel moment frame, 20-story steel moment frame. You know, this was not an extensive exploration, but we can see immediately that due to the directivity effect that builds up towards the southern end in the fault normal displacement pulse, you have differences in interstory drift demand of about a factor of 4. And that wasn't an extensive search. There will be areas where it's even more than that. And so the kind of things that simulation can help us understand, because we'll never have enough data to do this, is these kind of things. What's the inner event, within event, and between event variability, which will better inform how we think about our design criteria, in my mind, moving forward. So I'm going to end it there, and we're going to ask Arvin to come up.